So welcome to this week's Idaho Water Resources Research Institute seminar, and I'm happy to introduce our speaker today. Tao Huang is a new faculty member here at Idaho State University, where I'm based as well. And he just joined us about a month ago. He completed his undergraduate and master's work at Tsinghua University in China, and then a PhD at Purdue University. After that, he headed to the Pacific Northwest National Labs, where he worked on large data sets. And I wanted to share with the group, here's in the chat, I threw a link to Tao's LinkedIn, where he's recruiting students to join his lab here at ISU on a couple of different projects that sound really neat. And I just wanted to highlight that he actually received the editor's choice for the best technical paper a couple of years ago for some of his work that I'm not sure we're going to hear about today, on improving our uncertainty estimation around flood insurance mapping. So without further ado, I am thrilled to introduce Tao.
Right. Thank you so much for the kind introduction, Dr. Sarah Garcia. I really appreciate for sharing the kind of linking website. And good morning, everyone. My name is Tao Huang. I'm a kind of brand new assistant professor in the water resources area of the Department of Civil and Environmental Engineering at Idaho State University. And I just joined Idaho State University last month. And as Dr. Sarah Garcia mentioned just now, I got my PhD in civil engineering, specifically hydrologic and hydraulic engineering from Purdue University, Indiana in 2023. And after that, I worked as a postdoc in Earth System Data Science at the Pacific Northwest National Laboratory for 2 years. And the Pacific Northwest National Laboratory is one of the 17 United States Department of Energy national laboratories, similar to INL, Idaho National Laboratory here in Idaho. So very happy to be here today and have the opportunity to share some of my work over the past few years with you guys over Zoom. So the topic we'll talk today is about mechanisms of water, from hydrology and hydraulics to hydropower. I would say each word with the first letter H is a broad domain. I cannot cover any single one within just 15 minutes. So what I'm going to present today is just a small portion for each category. But alliteration works here, right? The same goes to my last name, Huang, which also has a first letter H. And in terms of happiness, I remember somebody said PhD stands for permanent head damage. Well, that may be true, but a little bit negative, right? So I would interpret PhD as a play happy degree, and I personally enjoy the fun along the adventure of doing research about water. All right, so let's get started. And my talk today was divided into 4 parts. The first 2 parts about flood modeling are falling with the category of hydrology and hydraulics. Then the 2 parts about the environmental impacts of the hydropower systems are from the projects I had been working on at the Pacific Northwest National Laboratory. So let's move on to the first topic, uncertainty analysis in flood maps. Fall is coming, it's a little bit chilly recently, so let's start with a kind of a warm-up question. Can you guess what is the picture in the dash box in the middle out there based on the 10 kind of observed data points? I believe nobody could get it right except myself. Let's take a look at the answer. It's actually a picture of Michael Jordan and me. So I'm a basketball fan, by the way. So this picture is like an analogy to a hydrologic system, say a watershed or a basin. While I personally think a watershed will be way more complicated than this picture itself. So during the simulation of a hydrologic system, our numerical modeling process is subject to various uncertainty sources, including limited observed data, for example, only have 10 data points here to predict what the picture is, or data with much noise, and our limited knowledge, which leads to imperfect models or algorithms. I also found that the uncertainty model evaluation process should not be ignored. So next, I'll be talking a little bit about the uncertainty quantification, the context of FEMA's flood maps. Of course, FEMA here stands for Federal Emergency Management Agency. And I know flooding is an old topic for human societies, but it's still affecting people's life in different ways. As you can see in the picture on the top right, it's a severe flood event that happened in some regions of North Carolina last September, roughly 1 year ago. Roads and bridges were destroyed. The car almost got swept away by the flood water. So horrible, right? According to the data from NOAA, on average, about 145 people were killed annually in the United States over the past 10 years. Only heat claims more lives than flooding. But those are not just numbers, not just statistics. They're real lives, because one is too many, right? So the accurate and reliable flood prediction is very important for local communities. In general, the numerical flood models can help us analyze the river's hydraulic behavior and provide flood risk information to the local communities or the general public. And one of the key resources available in the United States is FEMA's flood insurance rate maps, in short FERMs, which are usually corresponding to 100-year and 500-year flood event zones. They're essentially binary flood maps. In other words, if you're living in the flood zone, you're under great flood risks. And if you're living outside the flood zone, okay, you are safe. But we have to ask a simple question. That's true? And the official flood maps are available from the FEMA Flood Map Service Center and the National Flood Hazard Layer, as you can see on the right. You can just enter your address of your home or a place of interest and press the search button. You can download the corresponding flood inundation maps for the place or the specific region of interest. And the red area in the FEMA's National Flood Hazard Layer, you can see on the bottom right, represents the regions where FEMA's flood maps are available. So far, they have covered more than 90% of the United States population, so they are playing an important role in people's daily life. However, the uncertainty in the flood modeling process of these flood maps is rarely investigated systematically. So the objective of this study is to try to kind of address the interesting research questions. Are firms really firm? In other words, to quantify the relative impacts of various uncertain sources in the flood modeling process and compare the performance of the FEMA's deterministic flood maps and our proposed probabilistic flood maps. And typically, FEMA's flood maps are obtained from a HYCRAS one-dimensional static flood model, and HYCRAS here stands for Hydrologic Engineering Center's River Analysis System. It's a software developed by US Army Corps, and it's commonly used to simulate the flood inundation maps. Of course, it also has other great features. And you know, each model, no matter how complicated it is established based on some assumptions or simplifications. So the flood prediction from one single model implementation, one single hydraulic model is subject to various uncertainty, including model structures, for example, the governing equations to control flooding process, and model parameters, for example, the roughness parameters that used to kind of categorize the resistance in the main channel as well as in the flood plan, and model input, in other words, the boundary conditions for the numerical models. As the old saying goes, don't put all our eggs in one single basket, right? Especially for flood modeling, which is a matter of life and death. So we need to put our eggs in multiple good and robust baskets. That's the reason why we want to use the multi-model method to kind of reduce the uncertainty from modeling process. Specifically, Bayesian model averaging BM approach is employed in this study. It's a kind of statistical method that combines the predictions from multiple members in our sample. And it not only provides a kind of weighted average of the variable of interest, for example, water stage, water surface elevation for flood modeling, but also provides a kind of statistical distribution of the variable of interest, and from which we can extract some useful information. And meanwhile, the distribution itself is also a measure associated with the certainty about the mean prediction, right? And at the same time, the uncertainty propagation can be also demonstrated and quantified through a so-called hierarchical BMA framework structure. So let's move on to the study area and data. According to the availability of FEMA's flood models, and the availability of the observed hydrologic data. 2 study rivers in the state of Indiana are selected as study areas for this study. And both rivers experienced 100-year flood events in the past, and they're flowing through the kind of residential area. So there are multiple bridges across the ridge. And in addition, they also have different main channel slopes and different nuances, which provide a kind of good test bed for this study. And the upstream streamflow data from the upstream USGS gauge are used for the upstream boundary conditions for the numerical flow model. And the downstream water stage data from the downstream USGS gauge are used for BMA training and validation. And as I mentioned just now, the HACRAS one-dimensional static flow model is used as FEMA's flow model. As you can see in the picture on the right, it's a river network for the one of the 2-star rivers, Deep River. Blue line represents the river center line, green lines are the cross sections across the ridge. To make the simulation kind of much closer to the physical process of a natural river, one-dimensional static flow model is converted to a unstatic flow setting without changing any major parameters. And for 4 months of the year of 2019 of the daily simulations were performed in HACRAS to estimate BMA parameters. And the results from the same period of the next year, 2020, are used for model validation. All right, let's move on to the kind of principle of the Bayesian model averaging approach. According to the law of total probability, you can see in the equations on the left, the probability of the variable of interest, which denoted as small y here, which is the water stage in the flood modeling process. And given observed data, big D, which is the daily water stage data from the downstream USGS gauge, can be estimated using the equations on the left. And one of the good strengths of the BMA approach is that all the BMA weights are non-negative, and we'll try to find out the BMA weight and variance for each model member in the sample, which reflect how well specific model predictions match the observation. And because all the BMA weights are negative and the sum of the weight is equal to 1, so it's relatively easy to interpret performance of the model member in the ensemble. So of course, because the value range is from 0 to 1, so the higher the BMA weight, the better performance the model member has. And we assume the conditional probability follows a Gaussian distribution, and we know it's not necessarily true for some hydrological variables, right? For example, rainfall and precipitation are always non-negative. So the distribution tends to be skewed to some extent instead of as symmetric as a normal distribution. So the box cost transformation method is employed to process or kind of transfer original hydrologic data from the original space to the Gaussian space. And in order to estimate the BMA parameters, namely BMA weight and variance for each model member in the ensemble, we construct a log likelihood function like this in order to find out a set of BMA parameters that can maximize the log likelihood function. And generally speaking, it's difficult to obtain the analytical solutions to the kind of log likelihood function or to the BMA parameters. So a procedure called expectation maximization EM algorithm was employed in this study. And I will not go into much technical detail of this EM algorithm, but we can think of it as a kind of optimization process to figure out a set of BMA parameters, weight and variance, which can maximize the log likelihood function. And in this study, the various uncertain sources in the flooding modeling process are classified into 3 general types. And regarding model structure, whether bridges are included in the flood modeling process is investigated, because in most cases, the information about the hydraulic structure, for example, the bridge geometry of the bridge piers or the elevation of the bridge deck, is not always available for some reason. And in terms of uncertainty in the model parameters, fixed magnitude and value, the original FEMA model, add significant uncertainty to the simulated results. So by discrete value ranging from 0.5 times n to 1.5 times n are used to incorporate this type of uncertainty in model parameters. And I would say it's a ransom range we can find from the engineering manual. And for the upstream flow input or input uncertainty in the input data, according to previous studies, the uncertainty or memory errors in the stream flow data is around plus to minus 10%. So 3 stream flow estimates here are used to account for this type of uncertainty in model input. So finally, 100 model configurations are created in HECRAS based on different combinations of the various uncertainty sources. And on the other hand, as I mentioned just now, we are also interested in how the uncertainty propagates through the flooding modeling process. So the different uncertainty sources are kind of separated at different levels. I can see in the hierarchical BMA structure right here. And the base level contains all the model members in the ensemble, which is 150 in this case. And models above are divided by averaging models one level below. So in this study, base level contains is set for flood plain roughness, and level 3, level 2, and level 1 set for channel roughness, upstream flow input, and bridges respectively. And I would say the order of the uncertain sources will not change the final results. It only depends on the kind of modeler's preference. And in the context of hierarchical BMA structure or framework, BMA weight represents the relative importance or relative contribution of the model among all the models at the same level or at the same branch. All right, let's move on to the results part. As you can see in the figures on the left, BMA weight and BMA standard deviation for each model member in the sample are shown here. You can notice that the highest BMA weight for the two-star river is 0.34 and 0.26 respectively. There is another kind of specific model that has a superior performance, say a BMA weight higher than 0.5. This further implies that it will be risky to rely on only one single model representation to generate flood maps. And then based on the kind of BMA parameters, weight and standard deviation obtained through the training period, the prediction attribution of the water stage for both the training and the validation periods can be obtained through a kind of random sampling procedure. You can see in the figures on the left, BMA mean predictions can match the observation very well, and the 90% prediction bounds can contain almost most of the observed data points. And the ranks in terms of the root mean square errors of the daily water stage for each model member in the sample are shown in the figures on the right. We can see that the BMA mean prediction may not always outperform all the other models in the sample, but it does become better than the original FEMA model as well as the sample mean. And again, we're also interested in how the uncertainty propagates through the modeling process and the relative impacts of various uncertain sources in the modeling process. So the BMA infrastructure framework or structure, as you can see here, is the results for one of the two-star rivers, Deep River. For example, if we take a look at the BMA weights at level 2 here, which is shown in the blue boxes, models denoted as Q-1.1 always get a higher weight, which means the upstream flow input should be a little bit larger than the measured values from the USGS gauge. Another possible reason is that this kind of larger upstream stream flow input could also incorporate the stream uncertainty associated with the stream flow input from the ungauged tributaries along the downstream ridge. And if we take a look at the level 1 here, model weights in the yellow boxes are here. Models denoted as B, which means this model includes information about bridges in the flood modeling process, also get a higher weight. So it would be better to incorporate this type of information on the process. This information is available. And all right, finally, based on the historical stream flow data, the 100-year BMA probabilistic flow maps can be generated, as you can see in the figure on the left. The probability of inundation is equal to the sum of the weights of the models that predict the specific region to be flooded. And then both the BMA probabilistic flow map and the FEMA's original deterministic flow map can be compared to the observed inundation stance, which is shown in the solid black line over here. And they're obtained from the high water mark data and Landsat images. You can see that both the thickness F and the correctness indexes in terms of the two-dimensional inundation stands of the BMA probabilistic flood maps are better or higher than those of FEMA's flood maps. And it's also important to highlight that the BMA probabilistic maps can also provide a probability of inundation instead of a simple yes or no answer to the questions about flood risks. Right, let's try to wrap up what we have discussed just now. And firstly, we classify the certain sources in the flood modeling process into three general types: model structures, model parameters, and model input. And secondly, multiple Heckless configurations are created based on the various uncertainties, based on the combinations of various uncertain sources. And then the prediction attribution of the variable of interest, for example, water stage or water surface elevation here, can be estimated through a Bayesian analysis as well as the observed water stage data from the USGS gauge. So we can create the statistical attribution, the variable of interest, which is water stage in this case. And the relative impacts of various uncertain sources can be demonstrated and quantified through a so-called hierarchical BMA structure. And finally, the BMA probabilistic flow maps can be created based on the sum of the BMA weights that predict the region to be flooded. So which can provide a kind of more comprehensive picture of the flood risks to the local communities than the conventional flood maps. Right, so this study is part of my PhD work, and it was published in American Society of Civil Engineers Journal of Hydrology and Engineering. And if you're interested in more details, feel free to check it out later. And as Dr. Sarah Gassi mentioned just now, and this paper is a great honor that this paper was awarded as the 2024 best technical paper of this journal. So feel free to check it out later. Right, so let's move on to the next kind of region-specific topic, flood modeling for Idaho. And speaking of kind of flood models, I would say we have a lot of options in our toolbox. So here is a useful and a computationally efficient one developed by the Pacific Northwest National Laboratory. I can see in the picture on the left, the kind of rainfall is transformed into the surface runoff based on mass conservation. And two rivulets, blue and green, flowing through the kind of terrain data, which is digital elevation model, DM grade. And the flow direction is determined by the kind of maximum downslope gradient, and the flow velocity determined by using the empirical Bayesian equation. And it's also important to highlight that this kind of approach or model can reduce the computational costs by 4 to 7 orders compared to the conventional hydraulic or flood model, which is essentially solving shallow water equations, right? And meanwhile, this new approach can also maintain the comparable performance in terms of the two-dimensional inundation stands and water depths for a specific location or region. So it provides a kind of great opportunity for efficient ensemble flood modeling, as well as the kind of probabilistic flood mapping that accounts for various uncertain sources in the flood modeling process. And I would say the kind of statistical rainfall frequency estimates, different kind of rainfall products are commonly used to kind of do the flood risk assessment and infrastructure design. But it remains a challenge to kind of translate the rainfall inputs into meaningful kind of flood maps. But by using the kind of model, computational efficient model I mentioned just now, we set up a kind of framework or pipeline that can explicitly account for the uncertainty, the rainfall frequency estimates from NOAA Atlas 14. You can see in the three figures on the left, these are the rainfall frequency estimates from NOAA Atlas 14 for the 1,000-year return period rainfall events with a 1-hour duration. Mean estimates the upper and lower bounds of the 90% confidence intervals. The input for this kind of framework are, of course, the rainfall estimates, different return period, frequency, and duration, as well as the digital elevation model, terrain data, specific region of interest, for example, the entire state of Idaho right here. And then the output would be the flood inundation maps I can see on the top right, which are the corresponding flood maps based on the 1,000-year term period rainfall events with 1 hour duration. So we can extract two-dimensional inundation stands for the entire area, as well as the water depth and the velocity of a specific region. And the preliminary results show that kind of relative difference in the inundation areas between the 90% lower and upper bounds of the 90% confidence interval are quite different from each other. I would say more work need to be done, more calibration and validation need to be done. But this effort enables local communities to kind of identify the high flood risk area, and also more informed decisions can be made in advance under varying kind of rainfall scenarios. All right, so let's move on to the next major topic about hydropower. And again, hydropower is not a new topic nowadays, but there's no doubt that hydropower is still the leading source of low carbon electricity generation around the world. According to the report from the International Energy Agency in 2021, I can see in the bar chart on the bottom right, hydropower accounted for about 60% of global electricity generation from all sources, and it's more than all the other renewable energy sources combined, like solar, wind, bioenergy, etc. However, the adverse environmental effects due to the kind of complex flow conditions in the hydropower systems are not negligible. And previous studies have shown that when the fish pass through the hydropower systems, they may be exposed to multiple physical stressors like rapid pressure changes, shear stress, or collisions, etc., which would result in fish injury or even mortality. We already have some kind of dose response models to kind of characterize the effects of biotrauma or shear flows. But in terms of quantifying the strike injury at a population scale, we still need to address the research question: how to predict the absolute strike injury rates or survival rates of the bypassed fish accurately and cost effectively. And with the kind of autonomous sensor fish technologies, again, developed by the Pacific Northwest National Laboratory, we can collect the in situ observations like pressure, accelerations, rotation, and temperature fish may experience along the fish passage. I can see in the picture on the top left here, which is a picture of the so-called sensor fish. It's simply a cylinder, a length roughly 10 centimeters. So it's initially designed to mimic the shape or the length of the jewel-shaped salmon. And the sampling rate of the sensor fish device is 2048 Hz, which means it can measure more than 2000 data points per second. So it can make full use of the data collected by sensor fish to better quantify biological effects of the strikes between fish and the rigid hydraulic structures, and further, yes, potentially reduce the substantial costs of the conventional experiments with a large number of fish. So typically the workflow is that we release the sensor fish through the turbine intake, and then it flows through along with the water and through the fish passage and starts to collect data during the fish passage. And once it comes out to the tail race, it will automatically float to the water surface and be recovered by the crew members in the boats downstream. And after being recovered and data is downloaded, and the same sensor fish is prepared to be released again, and so on and so forth. So the picture on the left also shows an example of the data set just collected by the sensor fish. And as you know, the conventional kind of live fish experiment could not present the hydraulic or physical conditions inside the fish passage. So we don't really know what's going on inside the fish passage. So it's not possible to determine which regions of the fish passage cause the fish injury or mortality. But a sensor fish can help in this case. So through the kind of analysis of the time series data collected by sensor fish, and multiple subregions of the fish passage can be kind of delineated or divided and used for identifying approximate locations where the severe strike events occurred on the fish. So in this case, for the Kaplan turbine passage, 4 regions are divided, as you can see here, from upstream to downstream, intake, wiki gate runner, and draft tube, according to the signature of the time series pressure curve. And in terms of the biological effects of the strikes between fish and the rigid hydraulic structure, intuitively, when the severe strike events happen on the fish, it will cause a kind of dramatic change in the velocity of fish, right? So we can get a significant peak in acceleration as well as in pressure, because velocity head is converted to pressure head when the severe strike event happen on the fish. So the velocity-based strike metric mv, I can see in the equation here, defined as a kind of integral of accelerations within short duration. And the pressure-based metric mp, defined based on the relationship between the changes in velocity and the changes in pressure head. So finally, the kind of survival rates of the turbine pass fish or absolute strike injury rate of the turbine pass fish can be estimated by using the cumulative distribution functions of the strike matrix. In other words, if the sensor fish from the turbine passage produce a kind of strike metric value higher than a specific threshold, it means the corresponding fish experiencing the same condition not likely survive through the fish passage. All right, let's take a look at some kind of results out here. So the intersection between the cumulative distribution curve of the strike matrix and the vertical threshold line, which is the threshold calibrated for the specific species juvenile Chinook salmon, is actually the estimated survival rates for different regions in the Captain turbine passage. So it's very clear that the runner of the new turbine passage demonstrated a better performance than the baseline turbine in terms of the fish survival rates. All right, let's move on to the last topic about hydropower yield detection from sonar data using deep learning algorithms. Since use are the kind of target fish species for conservation and of regulatory concern, and the accurate and efficient detection of migrating ewes is very important, and it can help us improve our understanding of ewes' behaviors and their interactions with the hydraulic structures like dam, right? And on the other hand, considering the kind of dark, turbid, and high flow environments, it turns out that the imaging sonar is a kind of reliable technology for the kind of fish passage monitoring. So, but oftentimes we have to look at the sonar images or videos and classify and localize the use and non-use manually. It's tedious and time-consuming, and sometimes it's easy to make mistakes. So in this study, we propose a framework by using deep learning for use and non-use detection automatically. So this framework, as you can see in the picture here, includes the procedures of converting sonar data into two-dimensional images, and then pre-processing sonar imagery to try to increase the signal-to-noise ratio to a large extent. And finally, multiple object detection for the use and non-use fish by using deep learning algorithm. And after removing the kind of noise in the sonar images to a large extent through image subtraction as well as wavelet denoising, I can see in the pictures on the left. The video on the right is a kind of example results of the yield detection from our proposed framework. And it's also important to highlight that the efficiency and accuracy of this framework are promising. And if the GPU resources are available out there, detection speed for this framework is roughly 10 milliseconds per frame or per image, which means it can process roughly 100 images per second, which is approaching the goal of the real-time detection. And in terms of the accuracy of this framework, in terms of F1 scores here, which is an evaluation metric combining the precision and recall metrics, we can think of it as a kind of true positive rate. And the value range is from 0 to 1, and the higher the better. F1 score here in our study is greater than 0.8, which is better than the kind of similar models proposed in the literature. So these two pieces of work were published a few months ago, and again, if you're interested in more details feel free to check out them later. And I believe they are open access articles. And of course, this work could not be done without the funding support from the United States Department of Energy, Water Power Technologies Office. All right, so I think I'm almost running out of time, so let me close with two interesting quotes. No one trusts a model except the man who wrote it. Everyone trusts a observation except the man who made it. Of course, our models and data and observations are not perfect, but we don't need to be kind of too paranoid about the models and data we're using. Because as George Box said, a well-known statistician, all models are wrong, but some are useful. So we just need to figure out and take full advantage of the useful models that fit the purpose, and then demonstrate their inherent uncertainty in terms of the kind of prediction over time and interpolation over space, and hence reduce the bias in the numerical modeling process. And last but not least, and a kind of shameless plug here, and again, similar to the LinkedIn website, if you're interested in joining me here at Idaho State University to kind of explore and learn more about the hydrology world through numerical modeling and data-driven approaches, feel free to reach out to me. And I'm also open to any kind of potential collaboration opportunities, guys here in Idaho. Right, so I think that's all I want to share with you guys today, and I'll be happy to take any questions you may have. Thank you very much.
Wonderful. Thank you so much, Tao. I hope that folks will feel free to jump in. You can either raise your hand or throw your questions into the chat.
Yeah, sure.
I'll try to keep an eye on that for us.
Thank you.
So I guess I'll start out while we're waiting for folks to get their questions in. What project or projects are you most excited to be getting started right now, Tao?
Maybe just the second topic, the region-specific topic, kind of develop is the foundation maps for the entire state of Idaho by incorporating the uncertainty in the rainfall frequency estimates from NOAA Atlas 14. And now you know the conventional FEMA flood maps are essentially binary maps, not actually so true in terms of the different various uncertain sources in the process. So a basic flood map may be a better way to incorporate this kind of different uncertain sources and provide more useful information to the general. So that may be one of the easy start for me because I have experiences in flood modeling. At least.
Yeah, and sounds really useful too.
Yes, because it remains a challenge because we already have all kinds of different rainfall products from remote sensing or from other traditional statistical methods, but it remains a challenge to kind of transform the rainfall to the maps, which is especially important, especially under different kind of scenarios, under maybe climate change or different change in the human activities.
Excellent. I see a few folks with video and hands raised. Bruce, do you want to jump in?
Sure. Can you hear me okay?
Yes, I can hear you.
Tao, really enjoyed your presentation. A lot of good information there. On your HEC-RAS modeling and uncertainty, as we transition from 1D to 2D HEC-RAS, do you think that will reduce the uncertainty or just add different types of uncertainty based on like grid sizes and so forth?
Yeah, I think though that's a great point. You know, 1D and 2D based uncertainty, the model structure the equation for 1D and 2D tend to be a little bit different. I would say for some area like a shop valley, I hear some echo out there, but anyway, yeah, maybe the difference between 1D and 2D are not significantly different, but for the plan zone, flood plan, or the urban area, which has a relatively small changes in elevation, I think the difference in the 1D and 2D will be quite different. So this is also a type of uncertainty we have to consider when we try to use this framework to the larger domain or to the other locations. So that's a great point. So of course, some area, especially for the coastal area, as far as I know, what FEMA are using are just two-dimensional flood models. So we have also considered uncertainty in terms of the 2D model. And one of the kind of advantages of 1D model is that it's pretty efficient. If everything goes well for the kind of study area, as I mentioned in this presentation, it just takes within 1 minute to finish the simulation. So we can guess the output within a short period of time instead of using a 2D model, create the mesh, also incorporate uncertain sources into different size of the mesh, right? And also it takes a longer time to finish the simulation. So we have, it's basically a kind of steeper learning curve by using 2D compared to 1D model. So again, there's always a trade-off between computational efficiency and the kind of simulation decision accuracy, something like that. So we have to make a kind of choice that fit the purpose.
So I heard a little echo from U of I. You guys were unmuted. Was there a question there, or should we move to the ones in the chat?
No, let's move to the ones in the chat.
Okay. So there's a question from Brittany Slane, which is, have you found that the probabilistic flood maps change the way that policymakers prioritize mitigation projects?
Okay, that's a great question, a great point. Unfortunately, based on my limited experience, I haven't noticed any changes happening out there, at least for FEMA's flood insurance maps. But that's a kind of direction we should kind of work on, right? So actually, I think based on my experience, or you can check your phone, actually the prediction from the, let's say the weather is actually kind of probabilistic results, right? And people are used to kind of adapt to this kind of probabilistic results. But for the flood maps, actually, it's still the old days kind of types. So that's the direction we should work on together. Yeah, that's a great question and a great point, the future direction.
Right. And another question is, what skills, this is from a student, Anna Snydock, what skills do you think are the most important to develop to be a successful modeler?
Well, that's a kind of interesting question, and I don't think I'm the right person as a kind of new faculty member or early career researcher to answer or address your concern. But just from the kind of topic of my presentation, happiness comes in water, right? If you enjoy what you are doing and the curiosity is really the driving force, you can become a kind of whatever the definition of success is, a successful modeler as you can. As long as you work hard, as long as you enjoy the work you're doing and you're curious about what's happening in the natural world, okay, I think that's a great start point. And again, even though I think happiness is a great thing, is an important factor of the function of success, but we have to remember that along the way of doing research, we have to suffer a lot of frustrations or failures. Again, as the old saying goes, failure is the mother of success, right? And frustration and happiness is also the mother of happiness. And once you solve the complicated tasks step by step, and you can get a strong sense of accomplishment, of course, happiness come to play in these cases, right? I hope that kind of answer your question to some extent, but that's my perspective of view.
I love your joy around those days when things don't go wrong, when you're doing modeling work or other science. There's a question here from Ethan about what are the biggest challenges in communicating probabilistic flood risk to the public who may be used to seeing just the quote line on a map?
Yeah, that's also a great point. I would say I kept mentioning the kind of idea or the word flood risks during my presentation, but I would say what I've done before are just a part or a component of flood risk. It's just about hazards, right? We have to also consider the kind of vulnerability or exposure under the definition of the flood risk. Or if we kind of express the flood risk in a mathematical way, it's essentially a kind of product of the probability of the flood event and also times the consequence due to the occurrence of the severe event. So again, we have to be a good communicator to convey all the uncertainty in the numerical modeling process to the general public. It's also mentioned that flood risk is actually not as simple as hazards. It's actually a combination of multiple factors along the way, and also kind of also incorporate so-called kind of social maps in terms of the relative importance or the consequences due to the flood inundation to the public. And the product of these two flood hazard maps, as I mentioned in the presentation, as well as the effort from the, say, the social scientists or decision makers consider the relative importance of that specific region, and the combination of these two can final deliverable to the general public. I believe as long as we try our best to convey our work to the public in a kind of simple way and easy way, I think they should be able to kind of get the point of this type of probabilistic from maps, because I believe people already have the experience in terms of the prediction in weather, right? Chance of the rainfall tomorrow is 90% or 50%, whether I should bring an umbrella outside, something like that. So they should be, yeah, get familiar with this type of probabilistic from maps if we transform it into the real world soon.
Great. I actually have a follow-up on that. I'm not sure, Tao, if you were able to join a couple of weeks ago when we heard about the wildfire-ready watersheds approach in Colorado. And I was curious if you have done any work on the role of fire in changing the probability for flood risk in any portions of the US, or if that's something that you're considering.
Exactly. Unfortunately, I don't have any kind of previous experience in doing that related to the relationship between wildfire and the consequence due to the wildfire to the flood, inundation, something like that. But that's a great kind of opportunity we can maybe explore in the future. Yeah, that's a great maybe potential proposal. Thank you, Sarah.
Sounds fun. Are there any other questions from anyone online, or see one more from Bruce? Go for it, Bruce.
No one else has questions. I'll ask another one. So Tao, on slide 26, when you're talking about measuring the different parameters of fish passing through hydroturbines, you have a, I'm assuming, neutrally buoyant cylindrical object, your test device there, and it measures different rotations. So I'm kind of curious. I mean, obviously, fish passing downstream reorient themselves, their tail first, as they allow the flow go down, and they're more of an elliptical shape rather than a cylindrical shape, which would affect the forces acting on them, and they can control their movements a little bit. And so I guess ultimately my question is, has there been any work done to compare the accuracy of these measurement devices with actual fish going through the turbines on like strikes, you know, where they cut in half or damaged, or their mortality rate, to see if these are really doing a good job of accurately capturing what's going on in there?
Yeah, that's also a kind of great point, a great question. And actually, this is something I think my former colleagues at the Pacific Northwest they were doing this in the kind of lab setup. For this work I just presented, they basically will compare point estimates in terms of estimates from the sensor fish data and also the point estimates from the conventional lab experiments. I would say just based on the point estimate of the survival rate, the difference between the estimates from the sensor fish data is quite close to the estimates from the lab fish, conventional lab fish experiments. The difference just within 3%. It's pretty kind of acceptable in practice. But the point you mentioned is pretty good because you know shape of the cylinder is quite different from the shape of a true fish, right? And the cylinder itself can also not control its own tail first or head first or something like that. But trying to kind of prove that we can correlate sensor fish measurements to the lab fish results, at least at an acceptable threshold. Anyway, that's also a kind of something we have to work on in the future, because the former colleagues in the Pacific Northwest also developed a form in terms of sensor fish, which has a flexible form similar to a fish, like a use, snake-like use, or similar shape for a kind of juvenile salmon, something that have different sensors at the head part and tail part of this fish body, and try to capture variables similar to the variables or condition experienced from that fish. Yeah, that's a great question.
Thank you.
Thank you.
Great. Are there any last questions? Hearing none, I think we've reached our time anyway, now that I look at it. So thank you so much, Tao. And I hope everyone will join us again next week, where we'll hear about one of my favorite topics, intermittent streams, from Chris Yeager and Roy Sando. Thanks, everybody.
Thank you for your time.
Thank you, Tao. Wonderful talk.